Hello everyone. In this lecture we will be looking at what are known as similarity transformations. Just like we were talking about orthogonal transformations and unitary transformations, in orthogonal and unitary transformations their importance was that they preserve the inner product. In a similar way, similarity transformations, it preserves the eigenvalues of a matrix. Okay, so how do we go about doing that? So for that we need to understand what is a similar matrix. So let's say I have a matrix A, then another matrix, let's say A cap. Okay, I have a matrix A, and n cross n matrix A is already there with me, and there is another matrix called as A cap. This matrix is also n cross n, obviously. Then this matrix A cap is said to be similar to this matrix A if there exists some other matrix P, some other non-singular matrix P, that means the inverse of P exists, such that if I take the inverse, P inverse times A times P, that is equal to A cap. If this relationship holds good, then we say that A cap is similar to matrix A. Okay. So this kind of a transformation is known as a similarity transformation. That means a transformation which transforms a matrix to a similar matrix using a non-singular matrix P. So that kind of a transformation is known as a similarity transformation. So similarity transformations, they preserve eigenvalues. So if A is similar, A cap is similar to A, then A cap has got the exact same eigenvalues as A. If x is an eigenvector of A, then y is equal to P inverse x is an eigenvector of A cap corresponding to the same eigenvalue. So even though eigenvalues will be preserved, but the eigenvectors could be different, but we can find out the eigenvectors very easily. If we know the eigenvector in x, then all I need to do is just transform this x like this, P inverse with x, and that is going to give us y. So that is going to be the corresponding eigenvector. Okay, so this is important when we consider the diagonalization of a matrix. Now this is a very elegant theorem. So what it says is this: so if I have an n cross n matrix A, and that has got a basis of eigenvectors, so I have a matrix A which has got a basis of eigenvectors, then this similarity transformation, that is x inverse A x, this is going to diagonalize this matrix. So that means, now remember, this x is a matrix, it's a non-singular matrix because its inverse exists. So according to the similarity transformation, all I need is a non-singular matrix. That non-singular matrix P inverse AP, that is going to give us a similar another similar matrix. So the same relationship holds good also. That means this A and this D, this matrix A and this matrix D, they are similar. Okay, and because these two matrices are similar, then this is a similarity transformation. And because this is a similarity transformation, that means the eigenvalues of A are going to be the eigenvalues of D. And the beauty of this is, you are going to get a matrix. It's going to be a matrix which is going to be nicely diagonalized, and along the diagonals it is going to contain only the eigenvalues, everything else is going to be 0. Okay, so with the eigenvalues of A as the entries on the main diagonal, so you can diagonalize a matrix like this. So now the question is, how do you get this x? Very simple. This x we can get by simply taking the eigenvectors, by taking the normalized eigenvectors of the matrix A, and take this normalized eigenvectors, and using these normalized eigenvectors as columns, you construct this matrix X. And once you do that, you can easily diagonalize this matrix. And because it's a similarity transformation, it is guaranteed that the eigenvalues of A will also be the eigenvalues of D. We can actually try this out to check whether this really works or not from the example that we had done in a previous lecture, that was the ellipsoidal basin problem. So let me just go ahead and do that. I think I have the problem somewhere over here. This was the ellipsoidal basin problem. Yes, this is the problem. So this was an eigenvalue problem. Okay, this was an eigenvalue problem. So here this matrix, the A matrix A was this one. So what these small a, b and small c, these values are given as this. So from there we got the matrix A, because this is the eigenvalue equation. Okay, this is the matrix A that we are looking for. So let me just write this down using these values. Yeah, I have to just work this out here. Okay, so we have in this case A, the matrix A. Okay, let me just simply write this as A, matrix A. So what is this matrix A over here? Matrix A is basically this one. Okay, so over here this A, B and C, the values of A, B and C are 1, minus root 5 and 3. So when you substitute 1, minus root 5 and 3, when you substitute 1 here, so minus 2, minus root 5 here, so root 5 and root 5, and C is 3, so we'll get minus 6. So we have minus 2 and minus 6 here, and root 5 and root 5 over here. So that is going to give us A to be equal to minus 2 here, minus 6 here along the main diagonals, and the off diagonal elements will be plus root 5, and here also we'll have plus root 5. So this is the matrix A. Okay, and we know the eigenvalues here. We have already found out the eigenvalues. What are the eigenvalues in this problem? Yes, the eigenvalues are minus 1 and minus 7. Okay, the eigenvalues are minus 1 and minus 7. Corresponding to minus 1, the eigenvector that we had was C1. The eigenvector was corresponding to minus 1. The eigenvector was C1 root 5 1. C1 into root 5 1. And the eigenvector corresponding to this will be C2 1 minus root 5. Or I could just write it as minus 1 root 5. Okay, both will be correct. So these are the eigenvalues and these are the eigenvectors. Okay, now we have to normalize them. Okay, so the normalized eigenvectors we need to find out. The normalized eigenvectors. So first we'll have the normalized eigenvector x1. So what will this be? This will be simply this vector divided by its norm. Okay, the root over the norm. The norm, this is this vector divided by its norm, so that is going to be equal to root over root 5 square plus 1 square, which is going to be 5 plus 1, which is 6, so root over 6. So 1 by root over 6, 1 by root over 6, and rest everything will be just the same, so root 5 1. Okay, so this is x1. In a similar way, x2 also is going to be equal to 1 by root over 6. The norm is same in both the cases, 1 by root 6, and rest everything will be same. So we'll have a minus 1 and root 5 here. Okay, so you got x1 and x2. So now how do you get this x here? This matrix, this non-singular matrix x, how do you get this? This x, how do you get it? We simply take this one and this one. So first one, the first column, so that is going to be equal to root 5 1, and next one is minus 1 root 5. Okay, and then of course 1 by root 6 is there, which I'll take as common outside. So this is x, and we know that this x is orthogonal. It is guaranteed that x is orthogonal. I'll leave this to you to figure out why. A hint is you just look at this theorems which you had done in the previous lesson. Okay, so x is orthogonal. Okay, so if x is orthogonal, that means the inverse of x is easy to find out. if x is orthogonal, the inverse of x is really easy, because for orthogonal matrices the inverse is nothing but the transpose. So the inverse will be equal to root over 1 by root over 6, the same factor, and the transpose of this one, which is root 5 minus 1, and here we have 1 root 5. So this is going to be the inverse. You can verify for yourself just by multiplying these two. You will get the identity matrix. So this is the inverse. So you can see here, that's why orthogonal matrices are really important. So we really don't have to struggle with the inverse. Just take the transpose, that itself is the inverse. Okay, so we got x and we got x inverse. So now we have to make this undergo a similarity transformation. So what is the similarity transformation? X inverse ax. So let's find out x inverse ax. So x inverse ax. So this is going to be equal to x inverse x. We have this 1 by root 6, 1 by root 6. That's going to give us 1 by 6. Let's write this beforehand. And then x inverse, which is root 5, 1 minus 1 root 5. Then we have a. What is a? A is this. So we have minus 2 root 5 and minus 6. Okay, and lastly we have x. X is basically this. So we have root 5 minus 1 root 5. So this is what we have. So all we need to do is just evaluate this one. Okay, so that is really straightforward. It's a 2 cross 2 matrix, so it should not take much time. So the first matrix, root 5 1 minus 1 root 5. Then I multiply these two. You can try this out for yourself. The answer that you will get is, I already worked this out. This one, when you multiply these two matrices, you will get minus root 5 7 minus 1 minus 7 root 5. So this is what you will get. Okay, and now we multiply these two matrices. So we have 1 by 6, and when I multiply these two matrices, this is what you'll get. You'll get minus 6, 0 here, 0 here, and a minus 42. And when I divide this throughout, this is divisible by 6. So when I divide this throughout by 6, so you will get 6 by minus 6, we'll get minus 1, 0, 0, minus 7. And as you can see here, that this is a diagonalized matrix. Okay, so this gives us a diagonalized matrix, which is, of course, it is equal to x inverse ax, and also the best part is this is your lambda 1. Okay, and this is the other eigenvalue, because if you remember in the problem that we had done, the eigenvalues were minus 1 and minus 7, and we got those two eigenvalues, so we got a minus 1 and the minus 7. So that's your diagonalization. Okay, so this is the diagonal matrix. Very important, very elegant theorem. Okay, so if A is a real symmetric matrix, then the eigenvectors of A, they form an orthogonal set. Then we can form a new matrix, basically the same steps which I have used in the previous doing the previous problem. Okay, the same set of steps. So what I do is you write down the eigenvectors as the column. So this is what I have done here, writing the eigenvectors. So remember, this is not a element. Okay, it's just it's a column vector. So this is one column, this is another column, and so on. So each of these corresponds to each eigenvalue. Okay, then we need to normalize each of them. So in this problem, of course, we normalize this. We already normalized this. We normalize this over here in this step. So we normalize this and write this as x1 cap, x2 cap, and so on. So this gives us x. Okay, so each column is orthogonal and a unit vector, and then we know that X is an orthonormal system. Then X will diagonalize the real symmetric matrix in this way. So if we do a similarity transformation, then we'll get a diagonalized matrix. So it's the motivation here is to start with a difficult system, diagonalize it, and then obtain a similar system. So, and this similar system can be solved just by inspecting the problem itself. So now let's say we come to forms. Let us say A is a Hermitian matrix and X is an eigenvector which corresponds to an eigenvalue lambda. So Ax is equal to lambda x. This is the eigenvalue equation, and then what I do is I pre-multiply with x dagger. So x dagger Ax is equal to lambda x dagger x. So here x dagger x is going to give us x1 square, x2 square, and so on. You can verify this for yourself. Okay, so and this x dagger x will be always greater than 0. Okay, so hence from equation number 1 we obtain that lambda, okay, if I take this onto the other side, because this is just going to be a number, then lambda will be equal to x dagger Ax divided by x dagger x. Then this quantity which is in the numerator is known as the form. Okay, the numerator in equation number 2 is known as the form in components, in the components x1, x2, and so on. So when n is equal to 2, okay, if it's a n cross is a 2 cross 2 matrix, then this form has got 4 terms. You can verify this for yourself. X dagger Ax, what is x dagger? It is x1 star, x2 star, right? And dagger means it's a column matrix, so it becomes a row matrix because you have taken the conjugate and the transpose. A, these are the elements. So we have A11 when you expand this. So we have A11 x1 into A11 x1 plus A12 x2, right? And similarly open this up and then multiply this also, then you'll get overall this is what you'll get. You can verify this for yourself. Okay, just multiply all of these and you'll get these 4 terms. Okay, so when n is equal to 2, this form, okay, this quantity called as form. What is a form? Form is the numerator of this equation number 2. Okay, so you can use the form to find out the eigenvalues. Okay, so this will have 4 terms when n is equal to 2. Then we can generalize this. In general, the form has n square number of terms. You can see here, if n is equal to 2, the form has 4 terms. If n is equal to 3, the form is going to have 9 terms, and so on. So in general, the form is going to have n square number of terms. If both x and a are real, then this dagger, it becomes the conjugate, simply conjugate, and this entire expression becomes much simpler. It becomes like this. So this is known as the quadratic form. So now we can transform a quadratic form to what is known as a principal axis form. So a quadratic form which has got many cross terms, as you can see here. As you can see here, we have lots of cross terms. X1, okay, x1 is there, x2 is there, but here we have x1 x2 and x2 x1. So we have lots of cross terms. So we can go from this form, okay, this quadratic form, to another quadratic form which does not have these cross terms. Okay, so that is known as the principal axis form. So here the assumption is that A is this matrix A is real and symmetric, and that means A has an orthonormal basis of n eigenvectors. Then the matrix X with these eigenvectors as the column vectors, this is orthogonal. So the moment it is orthogonal, that means X inverse is nothing but the X transpose, which is good news for us. Then D is a diagonal matrix. So if D is a diagonal matrix, we know from the similarity transformation D is equal to X inverse Ax, and from here we get this. Okay, you can do this very easily. So we have this one. So we have D equals X inverse Ax. Okay, D equals X inverse Ax. So now what we can do is we need to do some kind of manipulation over here. So how we manipulate this is this equation we pre-multiply with x. Pre-multiplying with x. So we have x, and then already there was x inverse Ax. Okay, this is going to give us the identity matrix. So we have x D this is equal to, this is the identity matrix, so we have A x. Now you post multiply with x inverse. When you post multiply this, then this again is going to be the identity matrix, and as a result we'll get this expression. Okay, so we have A, this is going to be A is equal to x d x inverse. Of course there is an inverse because it's orthogonal, so this x inverse is going to become x transpose, so x d x transpose. Okay, so then we insert this one. Okay, we insert this A, over here, so we have x transpose capital X d capital X transpose x. Okay, so this is how the quadratic form looks like. Okay, this is how the quadratic form looks like using a diagonalized matrix. Okay, so this is what we have. So now let x is equal to capital XY. So we do a transformation. We do a transformation from x to y. Then this equation number 4. This is what you'll get in equation number 4. This is what you'll get. And I have just written down the steps. You can try this out for yourself. So all you have done is this x transpose. Okay, so there is a x here. This x I have replaced it with capital XY. X I have replaced with capital XY. Then whole thing is transposed. Then we have x d x transpose. Then here again we have x, that x I'm writing it as capital XY. So now this one, okay, I want to open this. If I want to open this, we use this result, that is A B transpose is equal to B transpose A transpose. The order gets reversed. So as a result, this is going to give me this quantity inside the bracket. This quantity inside the bracket is going to give me y transpose capital X transpose. So that's why you got y transpose capital X transpose. Then we have x, right? And this x and x transpose x, this is going to give us, because x transpose is x inverse, so this is going to give us the identity matrix. Okay, similarly over here, x transpose x, okay, that is going to give us x inverse x, that is going to give us the another identity matrix. So we have gone, so we have y d y. Okay, and when you write down this d, what is this d? D is a diagonalized matrix, so it will have only diagonal elements, lambda 1, lambda 2, and so on, lambda n, and everything else will be 0 because D is diagonalized. So when you open this up, you will only get lambda 1, y1 square, y2 square, y3 square, and so on. So you will only get the squares of these individual quantities, so you will not get any cross terms. Okay, so the form becomes much more simpler. So earlier we used to have, if whatever was the n value, the number of terms was n squared, but with using a diagonal matrix, the quadratic form, the form, it becomes much simpler. Instead of having n squared number of terms, it will now have only n number of terms. Okay, so equation number 5, there are no cross terms. So there's something called as a principal axis theorem. Exactly whatever we have done here, this is written in the form of a theorem. So suppose I have a real symmetric matrix A, which has got eigenvalues lambda 1, lambda 2, and so on, and the corresponding eigenvectors, which are x1, x2, and so on. Then if we can form an orthogonal matrix, okay, you normalize each of these eigenvectors and you form a matrix. This is an orthogonal matrix. Then this substitution x is equal to capital XY, it transforms this form, the original whatever was the form, this had n square number of terms including all the cross terms, this becomes this form. This is the principal axis form. So this is the quadratic form and this is the principal axis form. Okay, so this will have only n number of terms. Okay, so these are the this x1 cap, x2 cap, these are basically the normalized eigenvectors. So a quadratic form, it combines quadratic terms with linear terms and constants. So example is this. So what will happen if I put these quadratic terms equal to some value? So this is equal to, let's say, 1 or equal to 5. This is equal to 5. So what will that give me? It will give me a curve. Okay, it will give me a curve along the in the xy plane. It's going to give me a curve. So an example of this is this one, x square plus 3xy plus 4y square is equal to this. So how do you get this? From here we can directly get what is a. You can see this for yourself. Okay, so what did we have? Let me just go back to a previous result. There. Okay, so it's a, let's say we consider real we consider real matrix. So we have x, so we have x transpose a x transpose ax will be equal to, just write this down, this will be equal to a11, because it's real. Okay, it's a real matrix. These are, x is a real matrix, so real vector, so therefore x1 star is going to be simply x1. So it is going to give me x squared. Okay, let's take two variables, x and y. Okay, x1 is equal to x. We are considering n equal to 2, n equal to 2, x1 is equal to x, and let's say x2 is equal to y. We'll just write it like this. So this is going to give us x square plus we have a12 xy plus a21 also xy, because x2 x1 plus a22 y square. Okay, so this is what we have. Okay, so we're going to use this. Oops, my mistake. Let me write this again. So we will have x transpose a x will be equal to a11 x square plus a12 xy plus a21 also xy plus a22 y square. Okay, so this is what we'll be using over here. Let's go back to the example that we left. Okay, this example. Okay, so this is what we have here. So this is the quadratic form Q. Okay, so this is the quadratic form. Okay, because this appears in the numerator of lambda, that lambda expression. So this is a Q, this is the form Q. So here this is what we have. So what we can do is, this one we can write it as x square plus this 3xy, because it has to be symmetric. That means a12 and a21 they must be equal. So 3xy, I just divide this 3xy, I divide by 2, so 3 by 2. So we have a 3 by 2 xy plus again 3 by 2 xy. So 3 by 2 plus 3 by 2 is going to give me 3xy plus 4y square. So now if you just compare this with this, so you immediately see that a11 is equal to 1, right, because there is a 1 here, and this is a12 is 3 by 2, a21 is also 3 by 2, and a22 is 4. So you can just build the matrix A. So what is the matrix A? a11 is 1, a12 is 3 by 2, a21 is also 3 by 2, and a22 is 4. So this is the matrix A. So this is your x, this x transpose A x. Okay, so from here you can obtain this matrix A. Okay, so let's do a problem here. Find out what type of conic section the following quadratic form represents, and we need to transform this to its principal axis. Okay, so find out what type of conic section does it represent, and we have to transform it into its principal axis. So we have 17 x1 square minus 30 x1 x2 plus 17 x2 square equals 128. So let me just copy the problem. So we have this. So now what do we need to do? First part is very simple. You can use the form to obtain what is A. So here we have Q is equal to X transpose capital A X, and this is your Q. Okay, so here this is equal to 17 x1 square, and then this is the cross term. The cross term I divide by 2, so it's going to give me minus 15 x1 x2, and then again minus 15, but this time I'll write it as x2 x1, doesn't matter, plus 17 x2 square. So from here immediately we get this is A11, this is A12, this is A21, and this is A22. Okay, so from here we get immediately we are able to identify A. So we have Q is equal to X transpose is x1 x2, it's a row vector, then A, and A we have already identified the coefficients. A11 is 17, this 17. A12 is 30 divided by 2, which is minus 15, then again minus 15 here and 17 over here, and then we have X, which is simply x1 x2. Okay, so this gives us, from here we can easily identify, so therefore this gives us the matrix that we're looking for, this matrix A. It is simply 17 minus 15 minus 15 and 17. Okay, so now we have to find out the eigenvalues of this matrix. Okay, so to find the eigenvalues of this matrix A, to find the eigenvalues of this matrix A, so what do we need to do? We just need to take the modulus of A minus lambda 1. This must be equal to 0. So this is equal to modulus A. So we have minus, so this one is identity matrix, it's a diagonal matrix, ones everywhere, so only the diagonal elements will have to subtract lambda. So we have 17 minus lambda minus 15 and again 17 minus lambda. This is equal to 0. So from here we get, when we work this out, this is going to give us 17 minus lambda whole squared minus 15 squared is equal to 0. Okay, so you can simplify this, open this up, simplify this, and I'll leave this to you. You will get something like lambda squared minus 34 lambda square minus 34 lambda plus 64 is equal to 0. You'll get something like this. The steps in between, please do it yourself, and then again there are some steps in between, and you can factorize this, and this is going to be equal to lambda minus 2 into lambda minus 32 is equal to 0. Okay, so therefore immediately, the eigenvalues are, so you immediately see the eigenvalues. The eigenvalues are, the first eigenvalue will be equal to lambda minus 2 is equal to 0, so this gives us the first eigenvalue, which is equal to 2, and the second eigenvalue lambda 2, that is going to be equal to 32. Okay, so we got the two eigenvalues, lambda 1 and lambda 2. So therefore in the principal axis form, so therefore in the principal axis form. Let's again go back to the slides. What happens in the principal axis form? In the principal axis form, all I need to do is just multiply this, no cross terms, only y1 square, y2 square, and so on, lambda 1, lambda 2. Here in this case there are only two eigenvalues, so it will be just simply lambda 1 y1 square plus lambda 2 y2 square. So in the principal axis form, this very same quadratic form, okay, the very same quadratic form, it will be equal to lambda 1, which is 2 y1 square, plus lambda 2, which is 32 y2 square. Okay, so this is the same form, whatever form we have over here, this is the exact same form. Okay, and we can get an idea of the shape of this one. We can get an idea of the shape of this. So what kind of conic section is this? Very easy. All you can do is you can just use this principal axis form to find out what kind of conic section are we dealing with here. So let's say in this case this was equal to 128. Remember I said earlier, whenever you make q equal to some constant, that is going to give us a curve. Okay, so q is equal to this, which is equal to 128. As per the problem, it is equal to 128. Okay, so because it's 128, so therefore we can now use it. So from here we get this one, to divide this throughout by 128, this equation divided throughout by 128, so you'll get y1 squared divided by 64, y1 squared divided by 64 plus y2 squared divided by 4, which is equal to 1. Okay, so this gives us y1 by 8, y1 by 8 whole square plus y2 by 2 whole square. This is equal to 1. So this is the equation of an ellipse. Okay, so to answer the question, what's the question? The question is, what type of conic section are we talking about here? The conic section that we are talking about is an ellipse. Okay, so this is how you can use the principal axis theorem. Then yeah, another interesting problem. So we have this quadratic form. Okay, so this is a quadratic form, 3x square plus 2 root 2 xy plus 4y square. So there are three parts to this. By changing the coordinates, write q as a sum of squares. We have to write q as a sum of squares, which is easy because sum of squares means there are no cross terms. There are no cross terms means that we are in the principal axis form. So all we need to do is, just like in the previous case, convert this form from this quadratic form to the principal axis form. That itself will be the sum of squares form. Then sketch the curve q equals 1 for both sets of axes on the same graph, and which is the closest point on the curve q equals 1 to the origin. So let me just copy all of this to a new page. Okay, so this is the problem that we have to solve. So we have here q is equal to this. So first thing that we need to do is we need to identify this A, that matrix A, for which we have to find out the eigenvalues. Okay, so let's go ahead and do that. So over here, given q is equal to 3x square plus 2 root 2 xy plus 4y square. So this is equal to 3x square plus, break this up into two parts, root 2 xy plus root 2 xy plus 4y square, and we know that q is nothing but x transpose a x. So this one is x transpose is row vector xy, and then we know what is A. Okay, this is A11, A12, A21, A22. So A11 is 3, A12 is root 2, A21 is also root 2, and A22 is 4. X, Y. So this is what we have. Okay, so once we have got this, so therefore we have by the principal axis theorem, okay, by principal axis theorem, with a change in the coordinates, okay, with a change in the coordinates, with a change in the coordinates, let's say from x we go to x and y, we go to x tilde, y tilde, we can write down the same form. We can write down the same form as whatever will be the eigenvalues. From here we can find out the eigenvalues. Let's say the first eigenvalue is lambda 1, and instead of x in the new system it will be simply x tilde squared, and the other eigenvalue is lambda 2, and instead of y we'll call it as y tilde squared. So this is how it's going to look like, okay, as the sum of squares. This is how it will look like. So now the question is finding out what is this lambda and lambda 1 and lambda 2. That is easy. So first, to solve the first problem, we need to find out the eigenvalues of A. We need to find out the eigenvalues of A. That is again straightforward. A minus lambda 1 is equal to, determinant of that is equal to 0. So we have over here 3 minus lambda root 2 root 2 4 minus lambda. This is equal to 0. Okay, you can do the steps in between. I'll leave this to you, and eventually you should get something like this: lambda minus 5 and lambda minus 2. This is equal to 0, which implies that lambda 1 is equal to 5, and the other eigenvalue lambda 2 is equal to 2. So once we know these, then very straightforward, by the principal axis theorem, we just need to apply this. We obtain, because we need this as a sum of squares, so by principal axis theorem, so this is how it's going to look like: lambda 1 x tilde square plus lambda 2 y tilde square, and we have already obtained lambda 1 and lambda 2. So this gives us q to be equal to lambda 1 is 5 x tilde square, lambda 2 is 2 y tilde squared. So this is the sum of squared, the very same form that we have here, written as a sum of squares. This is what it looks like. Okay, so this, of course, it's an ellipse. You can actually write this as an ellipse. I mean, even though we'll do this shortly, but just to give us a feel for what we are dealing with over here, let me just quickly show it to you. So we have q is equal to 1, because that's the surface that we'll be talking about. That's the surface. Q equals 1. Very next problem, q equals 1. Okay, for q equals 1, for q equals 1, which implies q is equal to 5 x tilde squared plus 2 y tilde squared is equal to 1, and from here we can just write this as x tilde squared divided by this one. We can write it as 1 by root 5 whole squared plus y tilde squared divided by this 2, bring this down, so we have 1 by root 2, because I want to write this as a squared. This is equal to 1. So this is an ellipse. Okay, so this is an ellipse. So if you want to plot this, if you want to draw this, of course one of the problems again is to draw this ellipse, but let's just get a quick feel for this. So let me get the shape. Okay, so this is how this ellipse is going to look like, something like this. Okay, and we can locate the position. So we have, let's say this is the x tilde axis, and this is the y tilde axis. So we have these different points. This is one point, this is another point, this is one more point, and this is one more point. Okay, so we have here, you can work this out for yourself. So this will be x tilde is equal to 1 by root over 5. Okay, x tilde is equal to 1 by root over 5, because if I put y equal to 0 at this point, y is 0, y tilde is 0. So when y tilde is 0, then x tilde is going to be equal to 1 by root over 5, and this side it will be x tilde will be equal to minus 1 by root over 5. Here this will be y tilde will be equal to 1 by root 2, and here it will be minus 1 by root 2. So this is how the ellipse is going to look like. Okay, so now the next problem is sketch q equal to 1 for both sets of axes on the same graph, for both set of axes. Okay, so for this now we have to again go to the principal axis. Remember that problem on the ellipsoid basin. So we found the principal axis. So for this we need the eigenvectors. Okay, so we need the eigenvectors. So for this is part B. Okay, so we need to compute the eigenvectors. So let us say for the first case, lambda equals lambda 1, which is equal to 5. Okay, one eigenvector is 5, another one is 2. So lambda equals lambda 1, which is equal to 5. So from here we just use that eigenvalue equation. So we have a minus lambda I and so on. So this is going to give us minus 2 root 2 minus 1. I leave this to you to verify for yourself, and this is going to be x and y. This is equal to 0, 0. Okay, so this is what we have. So from here we'll get two equations. First equation will be minus 2x plus root 2y is equal to 0, and the second equation will be root 2x minus y is equal to 0. Both these equations are saying the same thing. Both these equations are basically telling us that y is equal to root over 2x. So from here we can get x1. So therefore we can get x1 as some constant c1. If I put x equals 1, y will be root over 2, and normalize this. So when you normalize this, so you will get x1 hat, okay, and this will be equal to this constant c1. If we set it to root over 1 by root 3, this will be equal to, this will be normalized. So we have 1 root 2. How did I get this factor? Again, I just computed its norm, okay, and divided by the norm. So the norm of this vector will be root 3. So divide by root 3. Okay, so we get this. In a similar way, similarly, the other eigenvalue lambda is equal to lambda 2. The other eigenvalue is 2. Again, this I leave it to you to try out for yourself. Similarly, the normalized x2 hat, I'll finally get this to be equal to 1 by root 3 minus root 2 1. Okay, I'm leaving this to you to try this out for yourself. So now all I need to do is just plot this vector and this vector. Okay, so that is going to give me the both the axes that we are talking about here. So because as per the problem we need to sketch q equals 1 for both sets of axes on the same graph. For both of the sets of axes on the same graph we have to plot. So this is x and y axis. So from x y axis we need to go x tilde y tilde. So we have x and we have y here. X tilde y tilde y we want. So how do you get x tilde y tilde? We need to first find out x1. So which is x1? X1 is this vector. This vector will lie in the first quadrant because both x and y both are positive. So y, the y component will be larger because y component is root 2. Okay, so this is how it's going to look like. So this is your x1 cap vector. The next x2 cap vector. X2 cap is equal to, it is along minus root 2 1. So x component is negative, and y component is positive, so it must be in the second quadrant. It must be in the second quadrant like so. Okay, so this is your x2 cap vector. Once we get these two vectors, then this axis and the other axis, these two give us the principal axis. So this is the other axis. Oops. Okay, so we got the two axes that we are looking here in this direction too. Okay, so it's in the other direction. So now this is your principal axis because your ellipse is going to be along this direction. So the ellipse will be something like this. It will be aligned along the principal axis. The ellipse will be aligned along the principal axis. Okay, this is how the ellipse is aligned, and as per our diagram here, this is the x tilde axis and this is the y tilde axis. Okay, so that takes care of the second part of the problem. Sketch q equal to 1 using both sets of axes. Okay, so this is what we have done. So now next part of the problem, then there's the next part. Next part is, what is the point, closest point to the on the curve to the origin. So on this curve, which point is closest to the origin? So we can see here this point, right? This point, let's say this point C, we call this point C, and similarly we have this point we call it as D. These are the 2 points which are closest to the origin. So we need to find out the locations, what are the coordinates of this point. In other words, this is what we need to find out. You need to find out in the original coordinate system, in the xy coordinate system, what are the coordinates of these points. Okay, so that's what we need to find out. Okay, so for this, what we can do is very straightforward. We already know what are these coordinates in the x tilde y tilde, right? Because if you just compare these diagrams, you just compare this diagram, okay, this is your point C and this is the point D. Okay, because this one is just rotated like this, so this is point C, the same point C. So in this system, in this x tilde y tilde system, the point C has the coordinates. What are the coordinates of point C? The value of x tilde is 1 by root 5 and the value of y tilde, because at this point y tilde is 0, so that value will be 0. And similarly D has got the coordinates. D has got the coordinates along the x tilde value will be 1 minus 1 by root 5 and the y tilde value is 0. So now all we need to do is we need to do a transformation. So if you want to get from x tilde y tilde from this coordinate system, if we want to move to another coordinate system, and that coordinate system is your, let's say, x and y. Okay, that coordinate system is x and y. So in that case, what do we do? So this is your so basically this is our starting coordinates. I think I should be putting it in the other way around. Let me erase this because I want to relate this to the equation that we're trying to write here. So the original coordinate system is x tilde y tilde. This is the original coordinate system, and this is the new in the other coordinate system. Which is the other coordinate system? The other coordinate system is xy. So what we need to do is we need to transform from x tilde y tilde till the xy coordinates. So how do we do that? So let's say in this coordinate system the vector is x. Okay, in this coordinate system the vector is y. Okay, so we want this to we want to undergo this transformation from y vectors y to vector x, and to do that we can use this relation x is equal to capital X y, okay, which is there in one of the slides. This transformation, this is how you do the transformation. X is equal to capital XY. Okay, okay, so we can use this. So we already know what are the coordinates in the x tilde y tilde frame. We already know what are the coordinates. All we need to do is just do this transformation. That is going to help us find out. Okay, so let's do that. number C. Problem number C. Problem number C for point C. Okay, the coordinates in the x tilde y tilde plane. X tilde y tilde plane. The coordinates in the x tilde y tilde plane is, we already know, it is simply 1 by root 5 comma 0. 1 by root 5 comma 0. So therefore the transformation is x equals capital X into y. Okay, so the corresponding coordinates that you are looking for, this is equal to capital X. And what is capital X? Capital X is, we can get this from the normalized eigenvectors. Okay, the normalized eigenvectors are these, so we can just get this from here, the normalized eigenvectors. So we have 1 by root 3, 1 by root 3. So we have 1 by root 3, we'll take it common here, and then this one, the first column, and this makes the second column. This is your X. Okay, X and Y. What is Y? Y is X tilde Y tilde. Okay, so now rest of it is very straightforward. All I need to do is just substitute. Okay, so this is going to give us 1 by root 3, 1 minus root 2, 1, and here we'll just use these coordinates, 1 by root 5, 0. Okay, and once we do that, we get something like this, 1 by root 3, and here we'll get 1 by root 5. I'll leave this to you to verify. Sorry, 1 by root 5 and root 2 by root 5, or simply I could just write this as root over 2 by 5. So I'll get something like this. Okay, so therefore the coordinates of C in the xy plane is, the coordinates of C in the xy plane is 1 by root 3, x coordinate 1 by root 5, and the y coordinate is root over 2 by 5. So this is what we get. Okay, in a similar way you can find out the coordinates of point D, which of course we can just guess from here. The coordinates of D will be simple because it's in the third quadrant, so you'll get minus 1 by root 3, 1 by root 5 into 1 by root 5, not into, comma, root over 2 by 5. Okay, I'll leave this to you for finding the coordinates of C in the xy plane. I'll leave this to you. Please work this out for yourself. And finally, this is the quadratic form. By changing the coordinates, write Q as a sum of squares. Very straightforward problem. Please try this out on your own. So with this we come to the end of this particular lecture. Thank you.